Good morning, friends and neighbors, and happy Friday. This is Professor Bruce Hartpence with another networking video. This week we are covering part 2 of the series on the Routing Information Protocol. Remember that this comes from Chapter 5 of the Packet Guide to Routing and Switching. Now, in the last video we talked about the basics of RIP operation, and we had this sample topology here. And as the routers exchange information, we know that the routing tables get built so that all of the destinations are included in the routing tables. So each router has a couple of directly connected routes, and then these RIP learned routes are also installed. The information is exchanged in update packets like the one you see here, and we know that this has the network information in it plus the mask and then the metric. And if you remember from last week, we talked about how every routing protocol has an administrative distance for RIP, that is 120. And then each routing protocol has a metric or metrics that it uses to describe the quality or reachability of the route. RIP uses 1, it's the hop count. And so each one of these advertised routes has a hop count associated with it. And that's really just distance away, or the number of routers you have to cross to get to this particular destination. But we have some problems here. Routing protocols, if left to their own devices, actually sometimes create problems. And so we make a lot of modifications to routing protocols. So the idea here is that if I took those routing protocols from our sample topology and just advertised those, it would actually cause some reachability problems. And what that means in this case is that routers would believe bad routes are okay. So let's talk about an example. That red X indicates that we lost the 4net for some reason. Could be unplugged cable, misconfiguration, whatever. And the router attached to that particular network would cease to advertise that network. Makes sense, right? But because the other routers are advertising their full routing tables, while router number 2 might not be informed about the 4 network from router number 3 now, it's okay because router number 1 has the 4net in its routing table, and he says, hey, router number 2, hey, it's okay, don't panic, I know where the 4net is. Well, of course he doesn't really. He's not connected to the 4net at all, but because he's advertising his full routing table, he sends that out. So obviously that creates a problem. Other improvements are designed to speed up the rate at which we converge to a stable topology and to handle looped topologies. First up is something we call split horizon. It's a cool name. But basically what it means is that don't tell me what I just told you. If you were introducing yourself to someone, you wouldn't say, hi, my name is Bob. And when they respond, hey, my name is Jim, you wouldn't expect them to say, oh, and by the way, your name is Bob, right? You just told them that. You don't need them to tell you what your name is. We apply the same sort of idea to routers. Router number 2 is in the middle of our topology. Router number 1 on the left there tells router number 2 about the 1 network. There is no reason for router number 2 to tell router number 1 about the 1 network. Why? Because the information came from router number 1. So that's what we mean by split horizon. It just basically says there's no reason to advertise networks to one side of the topology if you learn them from that same side. Now we see this in RIP packets because the routes are not actually part of the packet. So the 2 packets on the bottom part of this screen are the packets that were generated from the router interfaces that are connected to the same network. And we can see that in one direction, the 1 network is advertised, and in the other direction, the 3 and the 4net are advertised. And this is a really good indication that split horizon is active, that they're not advertising their full routing tables. And in particular, they're not advertising stuff that they learned from the neighbor. Another improvement that we have to routing protocols is the idea of poisoning. Poisoning simply means that when a router believes that a route is no longer available, that is, I can't get to that network anymore, it advertises the route as being unreachable. The mechanism that we use to advertise unreachability is by setting the metric to its maximum value. For RIP, which is a protocol used for small networks, infinity is actually 16. So anytime you see a network advertised with a metric of 16, you know that that network is actually being advertised as unreachable. Routers will do this when a link goes down, interface is shut down, or when the timers expire in a routing table and it doesn't want to advertise that route anymore, just simply from a lack of information. So this is an example of what we call poisoning. Poison reverse is a related idea. It's a variation on the theme. And the idea here is that even in an operating topology, when the route is still alive, the network is still reachable, you might not want to get to it from a particular router. And so that router would say, yeah, that route is alive, but don't try to get to it from me. Now, count to infinity is another tool that we have. Let's say that you're working in a topology and for whatever reason, some of our other techniques are not working or are not implemented. Well, if we just follow the basic rules and every router increments the metric by 1, we can see that the 4net here is being advertised to the left. Every router that this advertisement traverses increases the metric by 1. You can see that under normal conditions that the metric would increase. And every time an update came from our rightmost router, the same metrics would be in play. But if that advertisement didn't happen, the routers downstream, 3, 1, and 2, would continue to advertise this network. But it would be going around that loop. And every time it went around another corner, the metric would be increased until eventually the metric would reach 16 because the information wasn't refreshed from the rightmost router. And in that way, eventually, the metric would count to infinity, or 16, and then be dubbed as unreachable. And again, this might have happened because that right network went down. Now, another important part of routing protocols is not actually the message exchange itself, but rather what's happening in the routing table and the timers associated with those routing table entries. Triggered update is what happens when a timer expired or an event occurs. So for example, you down a link, we send lots of updates around the network because of that particular event. But at the same time, if for some reason you're not getting information about a network, eventually you time this network out of your routing table and then you send an update as a result of that timer expiration. The 3 basic timers that we have in RIP are the routing update or response timer, that's 30 seconds. So if you're watching a RIP network, you'll see about, on average, updates come from the routers every 30 seconds or so. A route timeout timer is the timer associated with a routing table entry for which we haven't heard very much information. So if a router stops advertising to me but doesn't poison the route, I'll keep it in my routing table for about 180 seconds. At about 180 seconds, I'll note that this network is suspicious, that I might not want to use it. And then finally, 60 seconds later, I have the flush timer where I actually delete it. I have an asterisk next to that one because the RFCs and implementation of RIP don't necessarily agree on what the timer values are. So if you're building your own RIP networks, it's helpful to take a look and see what your equipment is actually doing. Well, let's close up RIP today with a couple of other ideas associated with any routing protocol. One of the questions that we ask is whether or not our routing protocol operates or interoperates with other routing protocols, and RIP does. We have to tell RIP that you have to redistribute routes from another routing protocol, that you have to redistribute static routes, but there are ways to get routing protocols to interoperate. RIP does have interoperability with version 6, so that means that there's a RIP version 6 out there. And there's an example of a RIP version 6 packet. You can see that it's structured in much the same way, except it's IP version 6 addresses. In a looped topology, there may be more than one pathway to a destination. And if the destinations are equidistant, meaning that the prefix lengths are the same, they're both learned by RIP, and the metrics are the same, the RIP will actually do some load balancing for you. Well, that brings us to the end of the routing information protocols. I hope that you found these videos instructive. Remember that we were following along with Chapter 5 in the Packet Guide to Routing and Switching from O'Reilly. I will be continuing the series with OSPF next time, so stop on by for those. Remember, brucehartpence.com, we've got configs, so I'm working on those. I'm starting to add some capture files, lots of stuff on the resource page. And, of course, you can sniff around the channel here and see what other kinds of videos we have. Well, thanks for listening, thanks for watching, and may your packets always reach their destinations.